Okay, we are off to chapter 9 here. We finished up talking chapter 7, which was different ways that you could classify chemical equations or reactions. In this chapter, we're really going to talk about what's referred to as stoichiometry and doing calculations from equations, which will essentially put together a couple of things that we've been talking about in these previous chapters, specifically grams to moles and also balancing equations. So, what stoichiometry tries to sort of answer and the type of questions that you come across is if you have a chemical equation and you know how much, for example, of the reactants that you're going to start with, you can do some calculations to figure out how much products you would produce in that reaction. You also could, if you knew, for example, you did a chemical reaction and you know the equation for that reaction and you figured out how much product that you produced, you could back calculate things like how much of the reactants you started with in that particular reaction. So, stoichiometry is really just a calculation that we do to figure out all kinds of things in equations. And really, the idea of stoichiometry revolves around the balanced equation, which means that pretty much the first thing you should always do is make sure that this thing is balanced and that you have a balanced equation. Absolutely none of the stoichiometry calculations will work if you're not starting first with that balanced equation. So as we talked about in the previous chapters, that may require you to actually write the equation from words. So you want to make sure, again, that you start with the actual proper formulas first and then balance the equation with coefficients. So remember, you don't want to do that at the same time. Try to balance the equation and write the formulas. Like your labs today, you have the front part, but you need to figure out what's on the right-hand side there of the arrow. You want to just start with the basic units of everybody, the ions if they're ionic, and put them together properly like we did with naming, and then go back and balance it. So again, that's really the proper way. The relationship that we could get from in a balanced equation does involve coefficients, and it's really no more than the actual balanced coefficients in the equation. We could say that in this case, 2 molecules of H2 react with 1 molecule of O2 to produce 2 molecules of H2O. The sort of stoichiometry relationship that we use pretty much in all stoichiometry calculations is what's sometimes referred to as the mole-to-mole relationship from the equation, and it is also just the coefficients. So we could say that for every 2 moles of hydrogen we put in there, we get 1 mole of oxygen with it, and we produce 2 moles of H2O on the back end. So in this chapter, this is pretty much what we will be focusing in on in terms of the relationship, which is that mole-to-mole relationship. This is the law of conservation of mass, which means obviously we don't lose any elements along the way, which means, again, if we had 4 carbons on the left, we would have 4 carbons on the right and something else, and they would have the same mass. So the mass of everybody should always add up to the same number. So what type of questions do we look for in stoichiometry? As I mentioned, really, if you just have one piece of information about anybody in that reaction or that equation, and you could get it to moles, you pretty much can then figure out pretty much everybody else in that equation. Uh, and when we look at stoichiometry, it is based off of the idea of perhaps they tell us in an equation, how much of A we're starting with. And maybe we want to actually know, how much of D we would produce. So really what stoichiometry is a way to go from, say, A to D. And it really is nothing more than just a conversion factor. And sometimes people get really freaked sort of the calculation, but it really is just a conversion factor. And the difference is instead of going to a table where it tells you, hey, 12 inches equals a foot, and you use that sort of equality as your conversion factor, where we get the conversion factor is from the actual balance equation. So that's sort of where we get the conversion factor to use in stoichiometry problems. Bless you. As I said, you can use it to figure out from A to D. You could also figure out from A to C. You could also start on the product side, go from like D backwards to either of the reactants and sort of figure out information. By the way, another thing that's commonly misunderstood sometimes about stoichiometry is when we do these relationships, people always think you got to sort of go across the arrow on one side to the next, and you don't. You could, if you had a question or needed to, just do the stoichiometry sort of relationship on the same side of the arrow, maybe between two reactants or maybe between two products. So you don't always have to do stoichiometry or cross over the arrow to do those calculations. You could do it really with anybody in the equation as long as you have that sort of piece of information that allows you to do so. When we do stoichiometry problems, and we're going to do stoichiometry problems in a number of chapters coming up as well. These are going to be more sort of traditional ones where we go grams to moles. But we can use any type of units. When we get into gases, we'll use like volumes and try to figure out those type of things. We will also, when we get into solutions, use molarity and volumes. So they can be any type of units. But really, as we'll see here in this chapter, as we'll see when we get to those chapters, the stoichiometry part of the calculation is pretty much the same. It's just kind of different in terms of the units of how you get to kind of the middle part of the sandwich, if the sandwich part there is really the same calculation. I will say in this chapter, most of the time, we're going to kind of do our basic grams to moles conversion and perhaps going the other way as well. A reminder, right, that to do that conversion, we go to the periodic table and grab the molar mass, right? And that molar mass is in grams per mole. It is the number right underneath the element there. And that is a very common sort of conversion that we use a lot in stoichiometry problems. Here is based on the mole method. We could use those coefficients as the moles of each of these, and we could come up with a lot of relationships and really conversion factors that will allow you to go from, again, one thing in the equation to something else. And typically in stoichiometry problems, you're given information about something you're really not interested in, but you got to kind of get to something you are interested in the equation. And once again, that equation is going to be used to sort of do that. These are 5 steps to basic stoichiometry problems. And I would say in most cases, step number 1 here, you probably won't come across a lot, but you will come across it occasionally. And that is a situation where you need an equation really to start a stoichiometry problem. And if you are, again, as I mentioned a second ago, given everything in words, you want to make everything into the proper formulas. And then you should definitely balance the equation or the reaction there. And I would say in most cases, you probably will be starting your problems right here with an equation. You just need to make sure it's balanced. So if you look at an equation, you see coefficients, probably going to be balanced. You should check it. I would definitely say if you look at an equation, if it's given to you and you see no numbers in it, no coefficients, you should take a pretty good look at it because it's probably not balanced. So make sure it always is balanced. The next thing you want to do is take whatever they gave you basically and convert it to moles. So whatever unit they gave you it in or whatever it may be, usually you'll need to do a conversion and eventually get it to grams and eventually probably take the grams to moles using the molar mass. So that's almost like after is whatever they give you, go to moles. The next step is really the stoichiometry part, which is you go to the balanced equation and you find the mole to mole relationship. And the mole to mole relationship is basically the two things you're interested in. One thing that you're interested in is whatever they gave you, and the other thing is pretty much what you're trying to find in the problem. Lastly, if you do all these steps, you should be in units of moles, and sometimes you will have to do some conversions on the back end into some other. You'd be going back from moles to grams. So a lot of times you'll be using the molar mass on the back end of the calculation as well. So really, in most cases, basic stoichiometry problems are really these 4 steps. Make sure you have a balanced equation. You want to convert to moles. You want the mole to mole relationship. And basically, you're going to take those moles to some other unit if necessary. These pretty much are the 4 basic steps to any stoichiometry problem that you do. And if you follow these steps in order, it should get you to the end in the right spot, hopefully. Now, it's also really important. Sometimes people do weird things like if something is done for you, just keep going forward in the steps, don't undo it. So, for example, if you're given something in moles, there's no sense of converting it from moles to grams just to convert it back to moles. Oddly, I've seen that done a lot in my past. So, obviously, if it's in moles, you just go to the next step and kind of continue on. But all basic stoichiometry problems pretty much boil down to those 4 steps and just follow them in the order. Any questions on that there? So let's take a look at an equation and really talk about how we could get these stoichiometric relationships from the equation and how we could use it. So for example, if we take this one equation and simply just looking at the coefficients here in this equation, we could come up with some relationships. For example, I could say for every 2 moles of CO I put in there, I need to put 1 mole of O2 in there. And again, that is just the coefficients for each of those in the balanced equation. I could also say for every 2 moles of CO I put in there, I should get out 2 moles of CO2. I could also say for every 1 mole of O2 I throw in there, I should get 2 moles of CO2 out. These are all what are referred to as being equalities, are stoichiometrically equal to each other. They are not equal to each other. Obviously, 2 does not equal 1, but they are equal to each other in the sense of proportion that you need to throw in there to get this reaction to take place. So it's kind of like when you make baked cookies, you got so much flour you got to throw in there, chocolate chips, right, and butter and all that kind of stuff to get like a dozen cookies made. And that's sort of the proportion that you need to kind of throw in there of each of these guys to get this reaction to sort of take place the way it's supposed to. Now, because these are technically equalities, like any equality that we talked about when we did like conversions way back when and dimensional analysis, we could actually write 2 conversion factors for each of these. So for example, we could say for the first one, in 2 moles of CO over 1 mole of O2 are 1 mole of O2 over 2 moles of CO. For the middle one, we could say 2 moles of CO over 2 moles of CO2, or flip it around, 2 moles of CO2 over 2 moles of CO. And lastly, we could say 1 mole of O2 over 2 moles of CO2, or 2 moles of CO2 over 1 mole of O2. These are 6 conversion factors that we could get from this one equation. So this one equation gives us 3 equalities, 6 different conversion factors that we could use in a calculation. Will we use all 6 of them? The answer is no. You're just going to use whichever one that you need for your calculation that you're doing. So you're just going to pick whichever one's appropriate. But these are all basically available to you to use. Any questions on that there? So for example, let's say in this reaction that we produced, I don't know, 87.5 grams of CO2, and we wanted to know how many grams of O2 did we start with? So this is going to be a stoichiometry problem. We're going to go through it here to see how those 4 steps work. So step number 1 is we want a balanced equation. So we have that done right here. We have our balanced equation. So that's all done for us. Step number 2 is to take whatever they gave us. In this case, we have 87.5 grams of CO2, and we want to know how many grams of O2 are we going to produce. So in this case, we do need to convert this into moles, which is the second step. So we're going to convert into moles. Obviously, to convert grams to moles, we will need the molar mass of CO2 from the periodic table. So we'll go to the periodic table there and get the molar mass of CO2. That's going to be 12.01 for our carbon, plus 2 times 16 for our oxygen, going to give us 4401 grams per mole as our molar mass for CO2. So we're going to use that as a conversion factor. So we're going to take the grams that they gave us, 87.5 grams of CO2. We're going to go opposites to cancel out the grams. So the 4401 grams per mole of CO2. The grams are going to cancel, and that's going to get us here 87.5 divided by 4401. We'll do a 1.9882 moles of CO2. Any questions on it that so far? The purpose of really doing the second step is you're just getting everybody into the proper units to do the stoichiometry part, because the stoichiometry part is always about mole to mole relationship, which means you need to get your number into moles so everything cancels out correctly. And that would be the next step that we would want to do. We would want to go to the equation for step number 3 here and find our mole to mole relationship. In this case, the mole to mole relationship would be what they gave us, which was CO2, and what we're trying to find, which is O2 in this case. We already did that right about here, right? And that gave us that equality. And it also gave us these two conversion factors down on the bottom here. And since I want to get rid of CO2 in this case and end up with O2, which conversion factor should I use? The one on the left or the one on the right? If I have CO2 and I want to get rid of it, which one should it be? Should be opposite, right? Which means CO2 should be on the bottom. So I would use this conversion factor here on the left. So I'm going to take my number that I have, 1.9882 moles of CO2, using, this is the big stoichiometry step. Don't blink, you'll miss it. It is here, just this conversion. And again, that comes from our balanced equation, is where we're going to get that from there. That is going to allow us to convert away from CO2 in this case, which is what we're not interested in, and then into O2. So we'll divide that by 2. And that's going to give me 0.9941 moles of O2. Now, if I wanted the answer in moles, I would be done. I could just put a box on it. But in this case, I do not want the answer in moles. I am looking for how many grams there are. So that would be the fourth step, which is, again, if you do everything correct up to this point, you should always be in moles, and we're going to take it to grams. This means that we actually need the molar mass one more time to do that. I need the molar mass of what thing at this point, though? I need the molar mass of O2, right? Because we have converted away from CO2. So I do have to go back to the periodic table to get my molar mass here of O2, which would be our 2 times 16, or 32 grams per mole. We will use that in our final fourth step here. We're going to put the grams up on top so that we end up with grams. Moles on the bottom so that they cancel. And in this case here, we will end up with 31.8 grams of O2. I'll just go above it. 31.8 grams of O2 in this case. And that obviously would be our fourth step. Any questions on any of those steps there? Now, I did it kind of step by step here, which I'm okay with. I know some people want you to do it all in one step, which you can. If you want to do this all in one calculation, you can start with this, then head over to here, then head over to here, and then to here. and not get a number in between each of the steps. It's perfectly fine. Just do it all in one dimensional analysis calculation. Perfectly good and fine to do so. If you do break it up by each step and get an answer, again, I would not round to the very end and take it to a couple of digits or so you're okay. Significant figure wise here, we only really had 3 significant figures with the 87.5. So that's why we ended there with 31, very badly written one, 31.8 grams in this step. Any questions on any of those steps? So once again, all basic stoichiometry processes, no matter how crazy the equation looks, no matter how weird the numbers may look, they're pretty much these 4 steps. You just follow it step by step. And again, it should lead you there to the end. Any questions on that there? All right, let's try some here and make sure. This is what we just talked about. So I'll just kind of scroll it across. That's the one. All right, so why don't you try this one here? We got lithium metal reacts with water to form hydrogen gas and lithium hydroxide. We're looking for how many moles of hydrogen gas can be formed from the reaction of 5.32 moles of lithium. So take a few moments and see what you come up with here. Okay, let's take a look, see how you're doing. So in this one, we obviously are not given the equation, but we are given it in words. So as I mentioned before, you definitely just want to start with the formulas, not worrying about the balancing part of it. So if I have lithium, a metal by itself, that is lithium with no charge, reacts with water, which should be H2O. To form means an arrow. Remember, hydrogen gas is not just H, but it is H2. And lithium hydroxide, lithium's +1, hydroxide's -1, which means when you put it together, you get something like this. So now that I am sure I have all the proper formulas down, then I should go back and make sure that it's balanced. It is not balanced in this case, so maybe like a 2 there, maybe a 2 there, maybe a 2 there. I feel like I'm just putting 2s, but hopefully that's enough 2s, I think. We got 2 lithiums on the left and right, 4 hydrogens on the left, 2 and 2 is 4, and 2 oxygens on both sides. So we are balanced. Any questions on that? So again, that is definitely always the order at which you should do that. Correct formulas, then balance. Now that I have it balanced, essentially I have 5.32 moles of lithium. I eventually want to find out how many moles of hydrogen would I produce. So now that we got the balanced equation, the next thing that we want to do is convert whatever they gave us into moles. Do I need to do that in this case? I do not, because it's already in moles, so don't undo it. So that means I go to the next step, which is really the stoichiometry step. So we're going to look at the equation and find the 2 things we're interested in. One thing is what they gave us, which would be the lithium. The other thing is what we're trying to find, which would be the hydrogen. And in this case, from the equation, we could see the coefficient is 2 for lithium. So that means for every 2 moles of lithium, I will get 1 mole of H2, which once again will give you 2 conversion factors at your disposal. 2 moles of lithium over 1 mole of hydrogen, or 1 mole of hydrogen over 2 moles of lithium. So we're going to start with what was given to us, which is 5.32 moles of lithium. We do want to get rid of lithium and end up at hydrogen, which means we do want to use a conversion factor here on the right, as that is opposite and puts the lithium on the bottom. And the moles up on top of hydrogen, that is again from the balanced equation. That is the big stoichiometry move right there. So we're going to take 5.32 divided by 2, gets us 2.66 moles of hydrogen. In this particular case, I am looking for moles of hydrogen, which means I am done. I can put a box on it. Yeah. In this case, I did not have to do the 4th step because I was looking for moles. If I were looking for grams, what would I have to do here at the back end if I wanted to get the grams of hydrogen? I would need the molar mass of hydrogen from the periodic table, and that would be the grams per mole, which will convert us back to grams. Any question on those steps there? All right. All right, so let's try another one here. Let's try this one, same equation. We're looking for how many grams of hydrogen if you started with 81.75 grams of lithium. So lithium is 6.941 and hydrogen 1.008. Once again, follow the 4 steps, balance equation, convert to moles, mole to mole relationship, and moles to some other unit. All right, so take a few moments there and see what you come up with here. We basically are starting with 81.75 grams of lithium. We want to know in this case how many grams of hydrogen. So it's definitely a stoichiometry problem. We're going to start with our steps. Step number 1 there is already done for us since we did it in the last one. In this case, we do need to convert right into moles since we were given basically grams of lithium. We would go to the periodic table here, right, and use the molar mass of lithium as our conversion factor. So we're going to convert to moles. So we'll take our 81.75 grams of lithium, once again using the molar mass from the periodic table. Grams are going to go opposite, so they cancel on the bottom. And if you get an answer at this point, you're looking at here 6.941, 11.778 moles of lithium. So that takes care of step number 2. Remember here, we ultimately want to get over to hydrogen. So this is where the stoichiometry part of it is, which again is pretty much just a conversion factor. So we'll go to our equation and look at lithium, which they gave us. We will look at hydrogen, which is what we're trying to find. And we will use the mole to mole relationship between those two that we get from the equation to do that. And that's the mole to mole relationship. And from the equation, we could see that for every 2 moles of lithium, I get out 1 mole of hydrogen. That again would give you 2 possible conversion factors, right? 2 moles of lithium on top and 1 mole of hydrogen on the bottom. Or you could flip it the other way with the 1 mole of hydrogen up on top and the 2 moles of lithium on the bottom. Continuing on here with our number. Since we do want to get rid of lithium, lithium does need to go in the opposite location on the bottom. And once again, this is the big stoichiometry move right there. Going in the equation, using it as a conversion factor. And that is going to get us here. We'll call it 5.8889 moles of hydrogen. And that would take care of step number 3. Any questions up to that point? Now, again, if I wanted moles, I technically would be done, but in this case, we do not want moles. We do want grams of H2, which means we do need to do really the 4th step here, which is take the units of moles. And as I mentioned before, you should always be in moles at this point, unless you did something incredibly wrong. But you should definitely always be in moles at this point. So we're going to take the moles in this point to grams, remembering that we are now at H2, which means we have to go back to the periodic table and get the molar mass of H2. Yeah. You would not. So that's a very good question. And it's something that we, I think, talked about when we did grams of moles and molar mass and all that. Whenever you do the molar mass, which is technically what this is, right? The molar mass. It should only really be done based on just the actual chemical formula, because you don't want to take the 2 into account there and then the 2 into account with the stoichiometry. You're going to be off. So regardless of whatever the coefficient is in the equation, if you need to use the molar mass as a conversion factor to go from grams to moles or moles to grams, should always be based just on the actual formula. That way you won't run into a risk of doubling it up here on the next step again. Yeah. Other questions? All right. So same thing here. We're just going to do it based off of H2's formula. And we would do our 2 times 1.008 for each hydrogen. And that'll give us 2.016 grams per mole. So taking our 5.8889 moles of hydrogen, use our molar mass. Here we are going to want the grams up on top, so we end up with grams, and the moles on the bottom so that they cancel. We will end up here with 2.016. I'll call it 11.87 grams of H2 in this case. And that would be our fourth step. This number that we get here is what is sometimes referred to as the theoretical yield. And that would be the theoretical yield in grams. By the way, that would be the theoretical yield in moles. A yield is a product. So what the theoretical yield is, and we'll talk more about it later on in this chapter, but what the theoretical yield is like your maximum amount of product that you should make based on how much you start with. If everything went perfect, there was no side reactions, you weren't a klutz and spilled it all over the floor, everything went perfect. This is in theory, which is why it's called theoretical. This is in theory how much grams you should actually produce in this reaction. It's like your maximum amount of product that you would be able to produce in this reaction. And that's really what these numbers mean, what we just calculated. It means that if we took 81.75 grams of lithium and threw it into this reaction, if everything went perfect, we should expect out 11.87 grams of hydrogen to come out of this reaction as a result of it happening. In reality, as we will talk about, which is sometimes referred to as the actual yield, things don't go perfect in reactions. So you very rarely get a perfect 100% yield. But the goal is to try to get as close as you can to that 100% yield, which is maybe what we'll be doing next week, or you'll be doing next week in lab, I think. Any questions on that there? Once again, it is these 4 steps. And like I said, I'm okay if you want to do a step-by-step and get an answer at each part. Again, just try not to round. But once again, as like in the previous one, if you just kind of want to wrap the calculation together, you could just do it all in one big calculation and just get the answer at the end. You do need to obviously show the steps there or the parts there, like dimensional analysis with the units and everything. But you can do it all in one calculation. Any questions on that there? All right, let's try a couple more here to make sure. Just the ones we just did. So hopefully we got the same answers. So that's good. Same answer. Good, hopefully. All right. All right, let's try this one here. We got this equation. If 765 grams of C6H12O6 is consumed by the body, how many grams of CO2 would you produce? So we're looking for grams of CO2. Carbon is 12.01. Hydrogen is 1.008. And our good friend oxygen is still 16. All right, so again, follow those 4 steps that we've been doing. Balance our equation. Convert to moles. Mole to mole relationship. And moles to some other unit. Okay, let's take a look and see. Obviously we got a stoichiometry problem happening. In this case, we again have some grams of our reactants. And in this case, we're looking for our grams of our products. So starting with the first step here, balanced equation, which it is. So that's good. Next step, we want to convert to moles. And once again, here we do need to do that since we are given it in grams. So we would need to find the molar mass here for this guy to convert it. That would be 6 times our carbon's molar mass from the periodic table, plus 12 times our hydrogens, plus 6 times our oxygen from the periodic table, That's like 180.2, I think, grams per mole. So we are going to use that as a conversion factor. So we'll take the 765 grams that they gave us. We will put the grams on the bottom so that they cancel out. 180.2 grams per mole. And if we get an answer at this point, 765 divided by 180.2, going to get us 4.2453 moles of C6H12O6. So that'll take care of step number 2. Now we come to really the stoichiometry part. We're not interested in this guy, but we are interested in the CO2. So we're going to use, again, the stoichiometry relationship or the mole-to-mole relationship. And from the equation, we can see for every 1 mole of the C6H12O6, we get 6 moles, in this case, of the CO2. So again, that's going to be our conversion factor that we're going to use to convert from what we don't want to what we do want. So 4.2453 moles of our glucose action. We want to get rid of the C6H12O6, so that should go on the bottom. And again, this is the big stoichiometry move or step. Just really this conversion factor here that's going to allow us to go from one thing to the next. And if we do that, that's going to get us there, times it by 6, about 25.4717 moles of CO2. This here would be our answer once again if we did want it in moles, but we do not want it in moles. We do want it in grams, which means we do need to take that extra 4th step here, and we're going to convert our moles into grams. At this point, though, we again need to remember that we are at CO2, so we have to go back to the periodic table and get the molar mass per the correct thing, and that would be our 12.01 for our carbon, plus 2 times 16 here for our oxygen, giving us 4401 grams per mole. So to finish it up here, taking our number, not too rounded, and in this case, the grams will go up on top so that we end up with grams. Moles will go on the bottom. The moles will cancel, and that's going to get us there. About 1,121 grams of CO2. Or if we're still significant figuring at this point, maybe like 1,120 grams of CO2 as 3 seems like the only number that we see here. So 3 significant figures would be good. Any questions on any of those steps? I'm hoping you can see a pattern that it really is just these 4 steps, regardless of what it looks like. Once again, this would be our theoretical yield in grams, and once again, that would be it in moles over there to our left. Yeah. Any questions on this one? And again, it means the same thing as we talked about before. If you did this reaction and threw in there 765 grams here, a little bit of glucose, you should get out about 1,120 grams of CO2 if everything went perfectly good. Any questions on any of those steps there? All right. One more here, maybe. All right, so we got this equation. We're looking for how many grams of cisplatin, whose molar mass is 300.1 grams per mole. If you started with 0.7752 of KT, K2PtCl4, whose molar mass is 415.1 grams per mole. Let's see what you come up with here. Okay, so let's take a look. Once again, we have 0.7752 grams of this guy, and we want to end up with the grams of that one over there. All right, so we're going to balance the equation, which it is, thank goodness, because it looks kind of scary. The next thing we're going to do is convert what they gave us into moles, which we do need to do. So we will start with our 0.7752 grams of K2PtCl4. They were nice enough to give us the molar mass here of that. And once again, if they didn't, you would need to go to the periodic table and calculate it yourself. Just add up all the parts, obviously, like normal. And in this case, we do want to put the grams on the bottom here, which is not that. There's close. Wrong spot for decimal. Try it again. 415, it looks like. 15.1 grams per mole of our K2PtCl4. And this basically would represent our second step here. Now, in this case, I'm not going to actually get an answer here in between each calculation. I'm just going to do it all in one calculation so you can see how it looks. So what happens at this point, right, is our grams cancel. And now we do need to do our stoichiometry part, which is the third step. And we would go to the equation and look at both of those things. And from the balanced equation, we could see that for every 1 mole of our K2PtCl4, we get 1 mole of our cisplatin, which is our PTNH3 2Cl2. So that's not too bad. So I'm going to use that as my third step. Again, you should be setting this up like dimensional analysis so we could clearly see that the moles of the K2PtCl4 is up on top, which means to get rid of it, we need to put it on the bottom here. And again, on top would go our 1 mole of our PTNH3 2Cl2 in this case. The moles will cancel, and that really is the big stoichiometry step right there. If we wanted our answer in moles, we technically would be done at this point. We could just get the answer, but we do not want moles. We do want grams. So we do need to go to our fourth step, which means we need the molar mass of what we're trying to get. And once again, they did provide that for us, which was nice. And if they didn't, you would need to go provide it for yourself there. So using that as our molar mass, we want the moles to actually cancel. So on the bottom would go a mole of our PTNH3 to Cl2. Up on top would go our 300.1 grams. The moles are going to cancel. That's going to leave us as grams, the only thing that's left. Just like a normal dimensional analysis, we're going to multiply across the top there. 0.7752 times 300.1, hit equals. Divide by 415.1. And that will get us here. Step 0.5604 grams of our cisplatin here. Put a PT in front of it there and a Cl2. And this would again be, in this case, because it is a product, that would be our theoretical yield in this case. So same 4 steps. Again, as I mentioned, you could just kind of do it all in one calculation, or you could break it up if it's easier so you do not miss any of the steps. Do it whichever way works best for you. For me, I don't really care. Any questions on any of that there? No. All right. Again, just one more reminder that we could use stoichiometry with anybody in the equation. It doesn't have to be, going across the arrow. So for example, if I did get the moles, say if we went back to this one habit, maybe, yeah. So let's just say on this equation here, where we got the moles of our CO2, and let's just say we wanted to know about water at this point. We could just actually pick it up here with the moles of CO2 in that previous problem, and we could go 25.5 moles of CO2. And now we could do the relationship between these two guys, and we see that 6 moles of CO2 equals 6 moles of water. So we could use that as a relationship. and go 6 moles of CO2 would give us 6 moles of water. Those will cancel, and we'll end up with 25.5 moles of water, which we then could use the molar mass of water, which is 18.02 grams per mole. And very quickly, because we know the moles of our product there, we can then figure out how many grams, for example, here, 459.5 grams of water we would also produce. So again, you don't have to go across the arrow. You could, as long as you can relate to anybody in the equation, reactant to reactant, product to product, reactant to product, product to reactant. So the usefulness of stoichiometry is it is nothing more than a conversion factor that allows you to go to anybody in the equation, and don't overcomplicate it. Yeah, sometimes people overcomplicate it, and it's really just nothing more than a conversion factor. Any questions on basic stoichiometry problems? All right. I think based on the time, this is probably a good place to lay it up.